At a residential construction site in the countryside of São Paulo, 5 bricklayers work side by side, building walls from 7 in the morning. On an improvised pallet beside the concrete foundation, stacks of red ceramic blocks measuring roughly 3.5 by 7.5 by 7.5 inches wait to be laid. A concrete mixer turns without pause, producing mortar. With each block laid, a mason's trowel scrapes away the excess mortar while someone checks the wall for plumb using a vertically stretched line. A wall covering 10 square meters, or roughly 108 square feet, requires an average of nearly 265 pounds of blocks and another 175 pounds of mortar. Once finished, that same wall will have to be cut horizontally to accommodate electrical conduits and vertically to receive plumbing, a process Brazilian engineers call wall chasing, which technically weakens what has just been built. Construction takes months. On the other side of the hemisphere, on a vacant lot in Ohio, a crew of 4 workers erects an entire single-family home in about 12 working days. Factory-cut 2x4 lumber, manufactured with millimeter precision, is assembled using pneumatic nail guns. OSB sheathing is nailed to the exterior, followed by a weather-resistant barrier, thermal insulation between the studs, and drywall on the inside. No blocks, no mortar, no concrete mixer. 2 homes, 2 countries, 2 methods that seem to belong to entirely different worlds. How did 2 modern societies arrive at such radically different building solutions? The immediate answer repeated in casual conversations is always the same. Brazil has a hot climate, so it needs heavy walls. The United States has forests, so it builds with wood. Neither explanation survives closer examination. Canada has even denser forests and temperatures that fall below -22 degrees Fahrenheit, yet it builds with wood. Germany has harsh winters and a forestry history similar to that of the United States, yet it builds predominantly with masonry and concrete. Brazil has vast plantations of eucalyptus and pine, particularly in the south, and still makes little use of this resource in housing. A country's choice of construction method is not determined solely by climate or the availability of raw materials. It is supported by an entire system made up of technical standards, labor, supply chains, financing practices, insurance, historical memory, and cultural expectations. Replacing brick with wood, or wood with brick, requires far more than changing the material used for the walls. It requires rebuilding almost the entire construction industry. And that, more than any climatic detail, explains why these 2 countries maintain building traditions so far removed from one another. Brazil's building tradition began taking shape before Brazil even existed as a nation. Portuguese colonists brought 3 construction techniques to the New World that had dominated the Iberian Peninsula during the 16th century. Rammed earth construction, made by compacting soil inside wooden forms. Wattle and daub construction, consisting of a timber framework filled with worked clay. And stone and brick masonry, inherited from a Mediterranean tradition stretching back through centuries to the Roman Empire. In the earliest colonial cities, especially Salvador, Olinda, and Ouro Preto, all 3 techniques coexisted. Wealthy churches were built of stone. Merchants' homes were made from reinforced earth. The poorest dwellings were built from unfired clay. Fired ceramic brick, the material that dominates Brazilian construction sites today, only became widespread toward the end of the 19th century, when the British established railways and textile industries in Brazil and brought with them stations, warehouses, and smokestacks built from solid brick masonry, many of which are still standing in cities such as Jundiaí, Sorocaba, and Juiz de Fora. This British industrial presence cemented the association between brick, permanence, and progress in the Brazilian imagination. It was the material the British used. It had to be good. The next transformation came with the industrialization of cement. Beginning in the 1930s, as domestic production of Portland cement expanded, Brazil embraced a construction system that would become its signature throughout the 20th century. A reinforced concrete frame made of columns and beams cast on-site, with ceramic brick infill walls serving only as enclosures rather than structural elements. It is Brazil's famous conventional construction system. Even today, it accounts for the overwhelming majority of residential construction in the country, from an apartment in Rio de Janeiro's affluent South Zone to a self-built home on the outskirts of Fortaleza. In this system, the brick does not carry the building, it encloses it. The building is supported by a network of concrete and reinforcing steel. That is why a wall can often be demolished during a renovation without causing the house to collapse, and why reinforced concrete became the silent language of Brazilian construction. There is also a second system, newer and less familiar to the general public. Load-bearing masonry, in which the blocks themselves carry the structural loads without intermediate columns. It was formally introduced in Brazil in 1966 with the construction of the Central Parque da Lapa housing complex in São Paulo. In 1972, 4 12-story buildings were erected within the same development, testing the limits of the system. In 1977, also in São Paulo, the country's first 9-story unreinforced load-bearing masonry building was completed using calcium silicate blocks. Beginning in the 1980s, hollow ceramic blocks entered the picture, and the system spread across the country. Today, cities such as Belo Horizonte, Goiânia, and Campinas contain residential buildings ranging from 10 to 20 stories, constructed with load-bearing masonry, and not a single conventional beam visible within their walls. The ABNT NBR 15812 standards govern their design and execution. It is a rationalized, industrialized system that is faster and less expensive than conventional reinforced concrete construction. Even so, for most Brazilians, the image synonymous with a strong home remains the same familiar one: brick laid in mortar, thick walls, and a heavy concrete slab overhead. The North American tradition of the single-family home followed an almost opposite trajectory. It also began with European colonists reproducing Old World techniques, in this case, the heavy oak timber frames typical of 17th century England and Germany. These homes, which can still be seen in parts of New England, used massive beams connected through traditional joinery and wooden pegs. Each building required weeks of work from highly skilled carpenters. The system worked while the American frontier remained small. It failed when the country began moving westward through successive waves of migration. In 1832 in Chicago, an engineer named George Washington Snow erected a warehouse beside the Chicago River using a technique no one had seen before. Instead of massive, carefully joined beams, he assembled a framework of slender, factory-sawn lumber placed vertically every 12 to 16 inches and fastened with inexpensive machine-made nails, which factories had begun producing on a massive scale. Balloon framing was born. 1 year later, in 1833, carpenter Augustine Taylor used the same method to build St. Mary's Church in the same city. Veteran carpenters ridiculed it. They said the frame was so fragile that the next gust of wind would carry it away. They were wrong. They were witnessing the invention of the modern American house. Beginning in the late 19th century, balloon framing evolved into platform framing, now the dominant system. The technical distinction is subtle but important. In platform framing, each story is assembled as an independent platform on top of the one below it. This makes the system safer against the internal spread of fire, easier for semi-skilled workers to construct, and more efficient when integrating OSB sheathing, insulation, and drywall. One statistic reveals the scale of the phenomenon. According to the National Association of Home Builders, in 2024, approximately 94% of all new single-family homes built in the United States used wood framing. Only 5% used concrete, and less than 0.5% used steel. This dominance is supported by an industrial supply chain that scarcely exists at the same scale in Brazil. Managed forests of fast-growing softwoods, particularly Douglas fir, southern yellow pine, and spruce, sawmills producing standardized 2x4 and 2x6 lumber in enormous volumes, factories manufacturing OSB panels and industrial nails around the clock, building material distributors in virtually every city, technical programs capable of training wood frame carpenters within weeks, and building codes such as the International Residential Code, which standardize every detail. When the two systems are compared under equivalent conditions, some differences become immediately apparent, while others prove less obvious than they first seem. A plastered ceramic masonry wall weighs between 40 and 60 pounds per square foot. An equivalent wood frame wall, with studs, insulation, OSB sheathing, drywall, and exterior cladding, weighs between 8 and 12 pounds per square foot. This means wood frame construction can use simpler and less expensive foundations, often a slab-on-grade foundation roughly 5 to 6 inches thick, compared with the more substantial foundations required for masonry walls. In terms of speed, a 1,000-square-foot single-family home built using Brazil's conventional system takes between 6 and 12 months to complete. The same wood frame home in the United States can be erected in 10 to 20 working days. The difference is not merely the material. It is the entire process. Electrical wiring and plumbing in a wood frame home run through the stud cavities without extensive cutting, demolition, or rework. In conventional masonry construction, pipes and conduits require channels to be cut into newly erected walls, increasing both material waste and labor. Thermal and acoustic performance is another area where intuition can be misleading. The heavy masonry wall familiar to Brazilians has considerable thermal mass. It takes time to heat up, and it takes time to cool down. In Belém, this can create discomfort throughout the day because the wall absorbs heat from the sun and releases it at night. In Curitiba, it can be useful because it delays heat transfer and helps preserve indoor temperatures when outdoor conditions change. A wood frame wall, by contrast, has very little thermal mass. It is lightweight. Its thermal performance comes from the layer of mineral wool, fiberglass, or expanded polystyrene between the studs, which resists the transfer of heat. When properly designed, this system can achieve a lower thermal transmittance than a conventional wall made from ordinary brick. When poorly designed, especially when insulation is inadequate for the local climate, it produces homes that are cold in winter and hot in summer. The same principle applies to acoustic performance. Masonry blocks sound through mass. Wood framing blocks it through a combination of layers with different densities. Either system can deliver excellent or poor performance depending on how it is executed. When it comes to fire, there is a persistent myth that must be dismantled. The structural lumber used in wood frame construction is pressure-treated when required and enclosed behind drywall, a gypsum board system designed to provide fire resistance. The complete wall assembly must meet the same code-mandated fire resistance requirements applicable to ordinary masonry walls. This is not bare wood left exposed to flames. It is a complete, enclosed assembly engineered to meet a specified performance standard. That does not eliminate its vulnerabilities. Wood framing is sensitive to excessive moisture when the exterior weather barrier fails. It can attract subterranean termites in tropical regions when preventive treatment is inadequate. Extreme winds can tear away roofs and compromise the structure in hurricane-prone areas such as southern Florida and the Gulf Coast. Masonry has its own weaknesses. Cracking caused by structural movement, thermal bridging through concrete columns and beams, water infiltration through poorly sealed joints, substantial material waste during construction, low productivity in traditional labor-intensive work, and renovations that are almost always destructive. Neither system is perfect. Each represents a different package of trade-offs. Regional variations deepen the contrast even further. In the United States, wood framing dominates from Alaska to Florida, but with significant adaptations. In California, where earthquakes are frequent, homes are reinforced with diagonal bracing and specialized foundation anchors. Their naturally low weight becomes a seismic advantage because lighter structures generate lower inertial forces as the ground moves. In Florida, post-Hurricane Andrew building codes adopted after 1992 require specific reinforcements for roofs, windows, and structural connections, while some coastal regions also use reinforced concrete for single-family homes. In the Midwest, where tornadoes are common, wood frame houses coexist with basements and underground storm shelters because no conventional residential building system can withstand a direct strike from a powerful tornado. Brazil's climatic diversity is equally extreme. In Manaus, where relative humidity remains above 80% for much of the year, the challenge is controlling mold and mildew in any building system. In Pernambuco's semi-arid interior, the problem is the daily temperature swing, from 95 degrees Fahrenheit at midday to approximately 64 degrees at dawn. Along the northeastern coast, salt-laden air corrodes metal components and deteriorates mortar with surprising speed. In southern Rio Grande do Sul, winter temperatures can fall to 23 degrees Fahrenheit under constant winds, yet conventional Brazilian homes rarely have adequate thermal insulation. Neither country is homogeneous, and no building system is neutral in relation to the territory where it is used. The meeting between these two models came late in Brazil, and it is still unfolding. The first wood frame home built in the country was erected in Viamão, Rio Grande do Sul, in 2001. For more than a decade, the system remained little more than a technical curiosity explored in graduate research. Beginning in 2011, after technical assessment documents were approved by Brazil's Ministry of Cities through the Brazilian Habitat Quality and Productivity Program, wood framing began to be considered as an alternative for affordable housing. In 2016, the Brazilian Association of Mechanically Processed Timber Industries created a dedicated committee to develop a national technical standard for the system. Companies from Paraná, such as Immergrün, which has operated since 2019, and developments such as Residencial Haragano, associated with the Minha Casa Minha Vida housing program, demonstrated that the method could work under Brazilian conditions when properly adapted. Adapting it to the tropics requires pressure treating the lumber against termites and fungi, using moisture barriers compatible with humid climates, and, in some coastal regions, installing cement boards instead of conventional OSB on exposed exterior assemblies. Copying the system without adapting it produces failures. Adapting it requires investment in local engineering. Some obstacles are not technical, and they may be the most difficult to overcome. Brazilian workers trained on masonry construction sites generally have little experience with industrialized assembly methods. Supply chains for standardized structural lumber remain limited and concentrated in southern Brazil. Banks and mortgage lenders hesitate to approve financing for systems they consider unconventional. Insurance companies may charge higher premiums. Market research shows that buyers still associate brick walls with safety and wooden walls with precarious housing, a direct legacy of old informal settlements built from loose boards, an image that has nothing in common with engineered wood frame construction. Symbolic infrastructure can carry as much weight as physical infrastructure. The present points toward a slow convergence. Pressure to decarbonize the construction industry, which accounts for approximately 40% of global carbon dioxide emissions, favors lighter, more industrialized building systems. Engineered timber, particularly cross-laminated timber, or CLT, is being used in buildings as tall as 18 stories in Milwaukee and Portland in the United States, and it is beginning to appear in experimental Brazilian projects. Light-gauge steel framing, the metallic cousin of wood framing, is also gaining ground on Brazilian construction sites. Building Information Modeling, or BIM, makes it possible to plan every component with factory-level precision. Digital fabrication produces pre-assembled panels that arrive on-site ready to be fitted into place. In the United States, stricter codes in regions exposed to hurricanes and wildfires are pushing builders to incorporate more concrete and masonry in specific applications. Following major wildfires, some California cities began requiring non-combustible exterior cladding even on timber-framed structures. Walls are no longer made from a single material. They are becoming hybrid systems that combine the strongest qualities of different technologies within separate layers. A home is not made solely from brick, wood, concrete, or steel. It is made from forests planted in Santa Catarina or Oregon, from clay deposits in São Gonçalo dos Campos or limestone quarries in the American Rockies, from cement factories in Sete Lagoas or OSB plants in Alabama, from roads carrying blocks to the outskirts of Recife or lumber to the suburbs of Atlanta, from technical codes written by engineers and debated in public hearings, from banks deciding which systems they will finance, from workers trained in vocational schools or directly on construction sites, and from collective memories of what a safe home is supposed to be. Every wall erected anywhere in the world carries this invisible network within it. A Brazilian who places a hand against the cool plaster of a brick wall in Uberlândia is touching 400 years of Portuguese tradition, a century of British industrial influence, decades of housing policy, and the memory of generations who learned to build one block at a time. An American who places a hand against the warm drywall of a wood frame home in Cincinnati is touching 200 years of westward expansion, industrial forestry, inexpensive nails, and a culture that learned to assemble houses almost like furniture from a catalog. Every wall holds the history of the place where it was built. If this kind of content resonates with you, subscribe to the channel and join us for the next investigation into how homes around the world came to look and function the way they do.